The following presentation is part of the Technology and the Corporation Conference Series, sponsored by MIT's Industrial Liaison Program.
Up on stage. Thank you all for being here to listen to me today. This is my first trip to Brazil, I have to say, my first visit here in Sao Paulo. I'm very happy to be here. I've enjoyed the 3 days I've had here so far, met a lot of wonderful people, and I've learned a lot about the local situation regarding water as well, which is quite challenging. I want to talk to you about one of the major challenges that MIT is thinking about these days. Professor Gleason, when she spoke earlier this afternoon, mentioned grand challenge problems that MIT is looking at. And after much discussion over the last 2 years or so, we concluded that water and food were severe problems for the 21st century. We feel that population growth, the rapidly rising world population, that development as people move to richer economies and richer diets, that urbanization, and of course on a longer time scale, climate change, are posing severe threats, unprecedented threats, to the world's ability to meet its needs for water and food. At the same time, we are optimists, and we believe that research and innovation, business development, and these factors and activities can help. We've always solved our problems before, and this is another problem that we should be able to solve. The chart that I'm showing here is from 2006. What it shows in red are areas where human use of water amounts to 100% of what we get renewably by rainfall over land. In those areas, we can consider to have water scarcity. These are, of course, long-term data, and often you will see in this graph they reflect high population density areas where there's so much demand for water that everything available is being used. One of the observations you can make immediately from this chart is that water scarcity can affect one part of a country and not another country, another part of the same country, that it can affect rich areas and poor areas, that it can affect areas that we would think of as being dry, such as the Gulf states or North Africa, and areas that we would think of as being wet, perhaps Florida, perhaps in other years, Sao Paulo. The point of putting up this variation is to emphasize that the problems that lead to water scarcity are different in every context, and that the solutions for them are different in every context as well. Of course, in Sao Paulo, you may have observed from this graph, the area around Sao Paulo is red, but it doesn't look so dramatic. Of course, that doesn't reflect the impact of drought. This is a photograph from earlier this year of one of the major reservoirs in the area. I'm told that in view of the rains that have fallen earlier this year, the reservoirs are now up to about 20% of capacity, but you're just coming into the dry season and there's still concern about water rationing. The important point about a drought, however, is that it tends to be a shorter time scale process. It's several years, perhaps, as in your case. When we look at other factors, they have longer time scales. Climate change, for example, will act over a much greater period of time. And we can look at the impact of human use over sustained periods. This was the Aral Sea in Central Asia. It was the world's fourth largest freshwater lake. There were cities all along the shore and fishing economies and shipping. The rivers feeding this sea were diverted for agriculture in Uzbekistan, and after 30 years, the sea has dried up. The boats now sit in the dust along the shores of what were once the shores of the lake, and the economies are wiped out. About 70% of the world's use of water is for irrigation, for agriculture. Much of that use is not terribly efficient use, and there's a lot of opportunity for innovation and improvement in the agricultural sector, which can help. But the biggest driver by far is our rising population. When I was born, roughly 1960, the world's population was 3 billion people. Today, the world's population is over 7 billion, and if I live to 2050, the world's population will be about 9.6 billion, which is to say the world's population will triple during one human lifetime. All of those people are going to be supplied by the same renewable source of water, which is rainfall over land. And that's a variable that goes up and down, but it's not a dial that we can turn up. It's more or less today what it was in 1960 when we had fewer than half the number of people. In addition, these people are increasingly living in cities, more and more of them. So what we have in a city is a very high intensity use, consumption of water, consumption of food, consumption of energy. A city by itself is not a sustainable thing. it relies on the surrounding lands to provide it with the water it needs, the food it needs, oftentimes the energy that's required. And so as we think about the rapid growth of cities, we have to think about how they can be designed to better manage resource consumption and to minimize waste. Now, we have done well so far in terms of our food production. World's population has risen, as I've described, and yet agricultural productivity has gone up almost linearly in time. The number of bushels of food per acre has risen constantly. And it's risen because of technology. It's risen because of the technology of synthetic fertilization. We use energy to produce ammonia through the Haber-Bosch process. It produces ammonia-based fertilizer, which gives plants their nitrogen. And so this ongoing addition of nitrogen, potassium, and phosphate has allowed us to raise agricultural productivity. But there are questions as to how much farther we can go. The world's population of 9.6 billion people will require perhaps 70% more food than we grow today. The reason for that being not just the growth of the population, but the transition to richer diets. When you move to a more meat-based diet, more grain must be grown to feed the animals. In fact, about 1/3 of the crops we grow today simply feed animals. When people move to a richer economy, they tend to move to a richer diet. Further, these fertilizers tend to run off into waterways, and when they get into waterways, they produce algal blooms that impair water quality and create other problems. This is a photograph of Lake Erie. It's one of the Great Lakes in the United States. It's about half the size of the Aral Sea I showed you a little earlier. And you can see here in 2011 algal blooms driven by agricultural runoff that cover much of the surface of the lake. This last summer, Toledo, Ohio, one of the cities in this chart, had to close its water system for a couple of weeks because of toxins from the algae. So we're reshaping the landscape as we do this. There are questions about our use of food as well. As it happens, we waste enough food to feed the world's 800 million hungry people. We waste enough food to feed them 4 times over. In the developed world, that food is mostly wasted at the table. In the developing world, it's mostly wasted on the way to the table, going through the farming. So we have challenges there about supply chains, about managing quality as foods are shipped and transported, and about preserving foods as they get to market. But for all of these comments, the world is covered in water. Some people say that our planet should not be called Earth, it should be called ocean, for reasons the picture makes apparent. As an engineer, as a person interested in water supply, one of the questions we might ask is, can we make water of this type usable by us? Can we make it drinkable? And can we do so in a way that does not produce excessive amounts of greenhouse gas and compound other problems? So at MIT, we looked at these problems and we decided to create a major new laboratory at the institute level called the Abdul Latif Jameel World Water and Food Security Lab. Like MIT's other initiatives, this lab works across the entire institute with faculty from all departments and schools. We engage everyone with the idea that putting a group of people together from different backgrounds is the best way to solve a complex problem. Our lab is new. It launched within the last year. And so what I'm going to tell you is why we think MIT is a good place to take on problems like this. What are the things that we've done so far that are important? Well, one important thing we've done is to work on technology for detecting leaks in water distribution networks. During my conversations here in Sao Paulo, I've been told that the amount of leakage is 30 to 40% of what goes into the piping system. That's actually not unusual by world standards. There's similar leakage rates all around the world. But there are cities that have worked hard to reduce the leakage rates and that have it below 10%. Some of my colleagues, Professor Andrew Whittle, has invented technology using low-power wireless sensors distributed through a piping network, which, together with data analysis algorithms, is able to localize and detect the presence of leaks in a network. He's developed this technology through an international collaboration in Singapore with our research partners there. And the technology has been deployed across Singapore. A company has been formed to commercialize this, and they're actually moving it on to Hong Kong. Another of my colleagues, Professor Kamal Yusuf Toumi, is looking at using mobile robotics to actually go in and find the precise location of the leak. Kamal has been working on this technology for roughly 7 years. He's got about a dozen patents around it, and this is also very close to being a commercial deployment. I mentioned desalination as a possibility, and so I want to say a couple of words about the issues in desalination. When you desalinate water, perhaps seawater, it comes into some type of a system, fresh water comes out, and you have a concentrated brine which contains the rest of the water and some of the salt, and all of the salts. It takes energy to do this, which a thermodynamicist might call work. And if you go through the basic thermodynamic calculations, you can find hard limits to the amount of energy that's required. They can never be done for zero energy, but it can be done for an energy of roughly 1 kilowatt hour of electricity per cubic meter. That's about the best you can do. There's no magic that will get you around that. I regularly see people with new technologies claiming they're going to cut that in half, cut that by a factor of 100. Thermodynamics prevents you from doing that. Today, however, we're operating at 2 to 4 times that energy level. And so there's a lot of room to continue to improve desalination technology to make it less energy intensive. Energy accounts for about 1/3 of the cost. You also want to have more reliable membranes and better processes, and I'll say a bit about that too. Now, desalination technology is already widely used, and it is already widely used in water-scarce areas. We did a small project in Copiapó in the Atacama Desert in Chile a couple of years ago to look at their water systems. Copiapó's river, which was its source of water, has been dry for 15 years. The water has been diverted for mining activities up in the Andes, and it's also been taken for agriculture. And as a result, Copiapó has moved to desalination. In this particular instance, they are taking salty groundwater with modest amounts of salt. They're running it through pressure vessels that contain polymer membranes. And by doing that, they are providing their groundwater, their drinking water supply, or part of it. One of the things we're very interested at MIT is then how to take a technology like this one and to improve it so that it consumes less energy and can be more efficient. I'm going to pass over this slide in the interest of time. One of the other things that's important in desalination systems is the survivability of membranes. There is a tendency for bacteria to grow on membranes and to clog them. Any wet system is going to have a problem with things growing in it. Karen Gleason, who spoke this morning, among her many other accomplishments, has used her ICVD technology to develop coatings for membranes that prevent bacteria from attaching. And when these coatings are applied to the membrane, the basic properties of the membrane are unchanged, but the bacteria are repelled. This is an example of a membrane with no coating. The white spots are bacteria, marine bacteria, that grew after 5 hours. The black one is a coated membrane. There are no bacteria after 5 hours. So it's an innovation. She describes how she gets to these things, which aims to limit the cost of the technology. There was a question earlier about hydraulic fracturing and its potential consequences for the environment. Hydraulic fracturing has been enormous in the U.S. To the point that we produce as much oil as Saudi Arabia now, and the Saudi king has refused to come and meet Obama, so they disagree, yada, yada. But the bigger problem here is that there is wastewater that comes up from the process, and it needs to be treated. So at MIT, we have a number of people who are looking very carefully at this wastewater and asking what would it take to clean it. In fact, if you look at these wastewaters, I've listed here the percentage of salt. 3.5% is like seawater. This is wastewater from Nova Scotia. This is wastewater from Pennsylvania's Marcellus Shale. This is wastewater from the Permian Basin in Texas. It's about 6 times saltier than seawater. And the energy required to separate it, I showed you that for seawater, maybe 1 kilowatt hour per cubic meter was needed. To clean up the water from Texas is more like 8 kilowatt hours per cubic meter if you have a perfect system. And so there are some significant differences to the technology and significant challenges. This is one system that was invented at MIT to look at that. So salty, very salty water is brought in. It's used as a coolant and a condenser. You top heat it. You spray it onto a splash packing. These packings are open. It's like a cooling tower fill, with the result that it doesn't have many problems with fouling and clogging up. In this system, you have air that circulates in opposition. Cold, dry air enters the packing. It leaves warm and moist. Water vapor is picked up. The vapor is condensed over here, and you have pure water at the end. And so this system is interesting because it's simple unit operations, it's robust. Oil fields are messy places. They work with equipment that can be beaten with a hammer. You know, you can't take something delicate out there. But this stuff is very straightforward. There is a problem. The problem is that a typical dehumidifier here has very low rates of heat and mass transfer. If you think about vapor in air and a cold surface, the vapor will flow to the cold surface and condense and leave as liquid water. Air is swept with it, and the air cannot be condensed. And so air piles up next to the condenser. It acts as a resistance to heat and mass transfer. So it's not a very good arrangement. But the innovation at MIT was to switch to a direct contact system in which warm, moist air is put into a pool of fresh water as bubbles. The bubbles form and break. There's no opportunity for air to accumulate at the condenser surface. And the air leaves the pool of water cooler and drier. So with this, you can make a system that's smaller, that's less expensive, and that's more efficient. The technology has actually, I'm not sure what's going on here. Oh, there we go. Has actually been commercialized. It's now deployed in West Texas. The students who invented this, they started a company, they raised capital. They now have 2 plants cleaning the water from hydraulic fracturing. You can see the result here. Professor Armstrong mentioned this invention that came from an MIT Energy Initiative-sponsored project. It refers to graphene membranes, single-atom thick sheets of carbon. And one of the important features of this type of technology is that you have very high flow rates of water for a given pressure difference. I worked with Professor Grossman. My students and his students got together. We asked the question, what happens if you have this very high flow rate, this flux of water, at a system level? Can you actually save energy in view of the system level thermodynamics? We found that for seawater, the energy savings were not so great, maybe 10%. But for brackish groundwater, such as I showed you from Copiapó, the savings could be more like 40% in energy. For seawater, the greater advantage is a much smaller system. Now, this technology, the people in the industry, they looked at this, they said, okay, some professors with a computer simulation, you know, let's see you make it and have it work. Well, Professor Rohit Karnik, my colleague in mechanical engineering, did exactly that. He developed ion beam technology for boring holes in sheets of graphene, and he has demonstrated salt rejection and effective use of graphene for desalination. Rohit has now started a company, and this will be spun out of MIT. As I mentioned, there are a lot of concerns about energy consumption and desalination, and so I'll give you another thought. The San Diego County in Southern California gets most of its water through long-distance transfers and aqueducts. The longer one runs from Northern California. It's about 500 kilometers down to Southern California. The pumping energy required to get the water to Southern California is as much as 2.5 kilowatt hours per cubic meter. Now, if you remember the numbers that I showed you for desalination energy consumption, 2.5 kilowatt hours per cubic meter is about what state-of-the-art reverse osmosis does today. And the result is that San Diego could replace this transport of water from Northern California by desalination, and it would be a carbon-neutral exchange. But it would leave the water in Northern California for the people up there who also are suffering from drought. San Diego will commission the largest desalination plant in the Western Hemisphere within about a year. Of course, the other aspect of aqueducts is that if there's no water up at the source, you don't get any water from the aqueduct. Now, wastewater is actually an overlooked and very important resource. It takes less energy to clean wastewater to the point of making drinking water out of it than it does to desalinate ocean water. It's about 0.6 or 0.7 kilowatt hours per cubic meter to clean this water up. So it's much more energy efficient to reuse wastewater than to move to desalination. You can't reuse all the water that you had because some of it's evaporated or spilled or lost through leaks, but you have a resource with your wastewater that can be treated and put to good use. Here in Sao Paulo, roughly 30% of the wastewater is currently treated. The rest is discharged without treatment. Now, In Singapore, they've taken this to an extreme. They currently reuse 30% of their wastewater directly into the municipal water systems. A lot of the use of this water is for industrial purposes. You replace industrial water by reuse wastewater. But they're expanding this to 50%, and it will include their drinking water systems. We're seeing this grow all around the world. In fact, San Diego County has just announced a large plant for reuse of wastewater. There's some interesting intersection of wastewater and biotechnology as well. At MIT, some of our former students have created a company called Cambrian Innovation, which takes the standard means of treating wastewater, which is to digest it with bacteria. You can collect methane gas from that, and basically you consume the biological components through digestion. But it turns out that if you get the right bacteria, they will not simply digest, they will generate electricity. And so these students have invented a product and started a company to treat wastewater, capturing the methane gas, but also generating electricity. Their technology is now working in a couple of plants in California. They're working with wineries and breweries because the wastewater from those things have very high levels of biological content. The bacteria just love to eat it. There's work on landscape architecture at MIT as well. This picture speaks for itself. Professor Ben Joseph did a project in Japan where he took a typical channelized waterway and he redesigned it so that it would actually have public park functions, so that there would be percolation and things growing on it. You can see that the buildings that were here before and after are still in the picture. And so what he's done is to go back in and rework a city. We've done this at larger scale, but for time issues, I'm going to skip that slide. We held another discussion at MIT. There is a problem on the Nile River. So I'm showing you the Nile River basin here. And on the Nile River, the Blue Nile branch starts in Ethiopia here. It provides about 60% of Egypt's water supply. And you can see in Egypt, the Nile River runs on here. It is their lifeblood. Egyptian civilization has always depended on that water. But now there is a large hydropower plant being built by the Ethiopians on the Blue Nile River. It will provide 6,000 megawatts, and they see it as incredibly important to transforming their economy. They're a poor country, and they need this energy. So Egypt and Sudan and Ethiopia have been in great conflict. The former government of Egypt under President Morsi had a simple solution for the dam. They were going to bomb the dam. Now a nation of 90 million people, a nation of 80 million people, you don't want to see those outcomes. There's a new government under President Sisi now. We held an expert workshop at MIT where we brought experts in hydrology, dams, water management, and climate change from countries unaffiliated with Ethiopia, Sudan, and Egypt. We had an unbiased technical assessment prepared. We shared this with the three governments in February. We know they received it and looked at it. Of course, they have their own processes, but they did sign an agreement to work on solving this problem during March. At an even larger scale, we have satellite projects we're doing with NASA. My colleague Darian Takabi notes that the most important interaction between the atmosphere and the hydrosphere, the water and the earth, occurs in the top part of the soil, where moisture evaporates, where rain is taken in. And so he's now got a NASA experiment that's going to measure the water content of the top 2 inches of soil over the entire globe. And from that, they will be able to do better jobs of predicting climate variability, water resources, and other factors. I want to mention 2 or 3 topics on food in the time remaining. Food waste is something I mentioned earlier, and it turns out that at MIT we have some interesting ideas here. My colleague Tim Swagger is a chemist, and he's interested in high sensitivity detection of chemicals in the gas phase. In fact, he was originally funded to detect chemical weapons, but he found that when fruit ripens, it emits ethylene. And he has a very simple sensor that's based on printing carbon nanotubes onto a piece of paper. When ethylene binds to the nanotubes, the resistance of the film changes. You can measure it with a voltmeter, and you can tell whether the fruit is ripening. This is a cheap technology. You could imagine putting it into every box of fruit you're shipping from a farm. And with this measurement of ethylene, you could determine which boxes of fruit need to be sold immediately, which are overripe, which need to be thrown away. This is also technology that MIT is spinning out. Now, we have all had the unfortunate experience of eating food which then makes us maybe not so well because of bacteria in the food. Wouldn't it be nice if you had something like a piece of litmus paper you could swab across a piece of fruit or across a piece of meat to determine whether there were salmonella or E. coli on this piece of food? Our colleague Karen Gleason has invented exactly such a sensor. In this case, she's deposited antigens to these bacteria onto a polymer film. When the bacteria bind to the antigens, the resistance of the film changes, and you can tell within 5 minutes whether you've got contaminated food. This is much faster than current assays for bacteria on food, which typically require sending a sample to a lab. I mentioned nitrogen fertilizer earlier. And wouldn't it be nice if we didn't need nitrogen fertilizers or if we needed less of it? My colleague Chris Voigt is a synthetic biologist. He's noticed that some plants, some crops, are very good at extracting nitrogen from the atmosphere. Legumes do this very well, but cereal grains do not. And so he's interested in coming up with hybrid strains of cereal crops that can do better nitrogen fixation so that you don't need all that nitrogen fertilizer. It would be transformative, it would improve waterways, it would cut costs, cut energy consumption. It's a grand challenge problem, and it's a difficult one. But he's working hard on it, and he's just gotten something like $25 million from the federal government to look at this. So I'm going to pass over a couple of slides here and begin to wrap things up. There are a lot of interesting things happening around food and around water. Some of the issues have to do with the question of how we use water and what is our infrastructure for water. Certainly, when you look at a water shortage, your first impulse should be to conservation. Just because you have a pipe system that allows you to hose down a sidewalk, maybe a broom is a good alternative. I spent many years in Southern California where every morning, in front of every major office building, there would be a man with a hose cleaning the sidewalk. Southern California is a desert. As I showed you earlier, all of its water is imported. In a way, it's almost disrespectful to the resource. And at this point, they've banned sidewalk cleaning with hoses in California. It's illegal. For other people who haven't got the infrastructure to use water, the intensity of water consumption is very low. For these people, the major challenge is to make sure that the water that comes home in that bucket is actually safe to drink. And technology is needed there. Perhaps, if you go to India, the mobile phone has very high penetration. It's possible to make sensors that can simply be plugged into the end of your mobile phone. And you put a drop of water on this, you may be able to detect whether there's bacteria in the water. Imagine some cheap technology that a person in a rural area who simply has the phone could use in order to make sure their family's water was safe to drink. And then I'll come back to something I mentioned a little earlier. This is a famous software entrepreneur. And he is just sampling water that came from reclaimed sewage. So his mind is open to these things. This, of course, is Bill Gates, who's also put a great deal of money into human health and other issues. So with these remarks, I'll stop here, and I'm happy to take any questions.